We're going to spend a few minutes on a tutorial about solutions, solubility, and a class of solutions referred to as electrolytes. Well, first of all, for most of us, when we're worried about solutions, we're worried about aqueous solutions. Most of us do our chemistry in water. And we're interested in looking at the concepts of solubility and insolubility of different materials in the solvents that we're dealing with. And is there a way to predict in advance whether or not a material will be soluble in the liquid system that we want to put? Well, when we're talking about solubility and our observations in the laboratory, like everything else, we're talking about energy. And we need to recognize that in terms of energy, the university always wants to run downhill. And by the universe running downhill, I mean that the universe is always trying to take systems and achieve a lower energy in those systems, which makes them more stable, less reactive, and taking the difference in energy and spreading that out in the rest of the environment. Often this includes increasing the entropy of the system. Entropy is one of our thermodynamic terms. And entropy corresponds to organization or complexity. It turns out that highly organized systems have a very low entropy because of that organization, and the universe favors chaos. And by breaking up organized complex systems into less systems with less order, less complexity, then that's a positive energy as far as the universe is concerned. It turns out that concentrated solutions of chemicals in the laboratory will spontaneously dilute whenever possible because concentrated solutions have a higher degree of organization, and the universe will always try to drive those systems towards less complexity, less organization, more chaos. Well, let's talk about why solutions form and how can we predict in advance whether or not solutions are going to form. Well, there's a very simple concept that's one of the first things that we learn when we're talking about solutions, called like dissolves like. And what that means is polar solvents are most likely to dissolve polar solids, and nonpolar liquids, nonpolar solvents, are most likely to dissolve nonpolar compounds. Well, hopefully you remember how to identify polar molecules from previous modules. If not, I would suggest you go back and review Lewis structures, and then finally how we're going to take Lewis structures and determine three-dimensional shapes based on those Lewis structures. Getting back to our water chemistry, water dissolves the following. Water dissolves glucose, a simple monosaccharide. Well, this 6-carbon monosaccharide has a large number of carbon-oxygen and oxygen-hydrogen bonds, all of which are polar. And those polar sites are capable of hydrogen bonding, and that means that every glucose molecule has 6 high-energy, very stable interactions with water molecules. That is why glucose is so soluble in water. Sodium chloride, an ionic molecule, as soon as it hits water, dissolves, and the sodium cations and the chloride anions immediately separate and start associating with water molecules. This gives us 6 high-energy ion dipole interactions. My ions are either plus sodium ions or chloride negative ions. And the dipole interaction portion of the interaction is provided by my water molecules. So we have 6 interactions with a sodium ion, 6 interactions with a chloride ion. But other ionic molecules like calcium carbonate, as it turns out, are not soluble in water. Calcium carbonate, the principal component in limestone, and also the principal component in any organism that forms shells, like oysters or clams. Well, if energy is the reason for everything, there must be an energy reason why one ionic compound like sodium chloride dissolves in water, but another ionic compound like calcium carbonate does not. And then finally, if we take a look at a hydrocarbon like octane, all carbon-carbon, carbon-hydrogen bonds, all of those bonds non-polar, that material is also not soluble in water. It's easy to see based on our rule of thumb, a polar solvent is unlikely to dissolve a non-polar material like octane. So at least our rule of thumb easily works there. Well, let's talk for a minute then about the energetics of solution formation. If energy is the reason for everything, we should be able to parse out individual energy terms that are going to tell us whether or not a material is soluble. The first energy term we need to consider is the energy necessary to break up either the intermolecular or ionic interactions for our solute. So the reason that we have a solid material is there's some sort of energy of interaction, energy of attraction between our individual glucose molecules. That will be an intermolecular interaction, or our cations and anions for something like sodium chloride. Going back, we can easily measure or calculate those interactions based on Coulomb's law for either full positive or negative charges, as we have for ionic molecules, ionic compounds, or our partial charges for intermolecular interactions. Anytime we have to invest energy, that's a positive energy term, and we have to invest energy to break these molecules apart. Similarly, we will have to invest energy to break up the intermolecular interactions of the solvent molecules. And it turns out for water, that energy of interaction between individual water molecules is quite high. It's a very stable system. And if we want to break the attraction of two water molecules to each other to insert something between them as we're dissolving our solute, we have to invest the energy to separate those two water molecules. Finally, we have a negative energy term, which is the energy of intermolecular interaction between whatever our solute is and the molecules of solvent. As long as we have an attractive energy, that will be a negative term as things are more attractive. So we have two positive terms where we have to invest energy to break interactions, and one negative term where we get energy back from making new interactions. Well, if the absolute value of the negative term is greater than the sum of the absolute values of the positive terms from breaking interactions, then the material will be soluble. And usually we'll end up with a system that is exothermic and will give up energy, usually in the form of heat, to the external environment. Not always. We'll talk about that in a minute. On the other hand, if the absolute value of the negative energy term of the interaction of the interactions that we're forming, if the magnitude is less than the absolute value of the positive energy terms, the energy we have to invest in breaking the existing interactions, then the material will be insoluble and endothermic normally. And again, there are exceptions to that. Overall, if we wanted to calculate the individual terms, we would say the change in energy or enthalpy of the solution is equal to the sum of these three energy terms, where one of the terms is negative, the solute-solvent interactions. The other two terms are positive, the interactions between solute molecules and then the interaction between solvent molecules. When we add up the three terms on the right-hand side of the equation, if the result is negative, the material should be soluble. If the result is positive, then the material should be insoluble. All right, so what's the exception to that? Well, many of you growing up playing sports have probably used these cold packs that you can buy in drugstores, where you have two different materials in the pack. You have some sort of liquid that's in a sealed container. You have some sort of solid. You don't know necessarily what it is. And if all of a sudden you sprain your ankle playing soccer and you need to apply ice, you can break that interior packet so the solid and the liquid mix. And then what happens? Does it evolve energy exothermic? No, in fact, it gets colder, indicating that the solution formation is endothermic. And it's trying to steal heat from the surrounding environment. It actually gets colder. So according to the equation we have written above, the solid material should not dissolve in the liquid, but in fact it does dissolve even though the overall delta H of the solution is positive, meaning it's an endothermic reaction and requires an external energy input. Of course, that external energy input is coming from your swollen, sprained ankle, and it's pulling heat, pulling energy out of that ankle. Well, how is that possible? Well, when we're looking at delta H, the enthalpy of solution, we're looking at bond formation. What we're ignoring in this equation for right now is entropy, organization, or chaos. It turns out for the cold packs that we're used to seeing, there are two different terms. And the reason that we have a positive delta H enthalpy of solution, but the material still goes in, is the organizational term entropy overwhelms delta H and the material still goes into solution. The entropy is driving that solution, and the enthalpy is clearly positive as we're trying to steal energy in the form of heat from your ankle. Okay, when we talk about solution equilibrium and solubility, we use some standard terms. What's the solubility of a material? It's the maximum amount of solute which will dissolve in your solvent. That's almost always temperature dependent, unless otherwise stated. We're talking about room temperature, 25 degrees centigrade. Precipitation, we have soluble species that meet up in a solution and form an insoluble product, and then drop out as a solid in the bottom of our beaker. Finally, we talk about saturated solutions, where we have reached the maximum solubility of our solute in solution, and we still have solid material sitting at the bottom of the beaker. So if I take a beaker of a liquid and there's no solid in the bottom, I do not know if I have completely saturated the solution, if I've reached maximum solubility. But if I take a beaker of solution and I can see solid solute sitting on the bottom, I know that the maximum amount of solute has dissolved in that solution. And of course, if I want more to dissolve for the vast majority of materials, I'm going to heat that solution up and drive more solute into solution. When we have excess solid sitting in the bottom of the beaker, there's actually an equilibrium set up between pure solid sitting on the bottom of the beaker and solute in solution. And under these conditions, we refer to the rate of precipitation, material coming out of solution forming the solid, being equal to the rate of dissolution, the solid breaking up and going back into solution. In this situation, we talk about equilibria being both reversible and dynamic in both directions. Okay, reversible means we can go in either direction. Dynamic means that this is constantly changing. So we also talk about unsaturated solutions, solutions who have not reached their maximum solubility. And occasionally we'll talk about something called supersaturated solutions, where through tricks in the laboratory, we've managed to get more solute into a solution than would normally be allowed. And there are reasons that we can do this in the laboratory, usually involving heating a solution up to dissolve excess material, and then slowly cooling that solution back down. And if we're very careful, we can prevent solid from coming back out of the solution, even though we're over the maximum solubility. In that case, we have a supersaturated solution. Well, depending on which textbook you have and where you look on the internet, there are general solubility rules. These are shown here from as a copy of the table in the textbook we're currently using. I'm not going to go over these rules in detail. You can look any of these up, and you should either have a table with you or attempt to memorize these. In general, any salts of group 1 elements are soluble: sodium, potassium, lithium, as well as any ionic materials that utilize ammonium, NH4+, as the cation. So sodium chloride, potassium nitrate, ammonium carbonate are all soluble. Ionic compounds that utilize nitrate ions, NO3- as the anion in the compound, are almost always soluble. Halides, chlorides, bromides, iodides are usually soluble, but not always. And now we start to run into some exceptions. Sulfates form soluble ionic compounds with, again, a number of exceptions here. Typical insoluble compounds are sulfides. Many of the mineral ores that we mine to make metals out of are, in fact, the minerals themselves are iron sulfides. The exceptions are sodium sulfide, see above. Sodium salts are soluble. Most oxides are insoluble. If we're mining metal ores and they're not sulfides, then they're almost always oxides, because sulfides and oxides of metals are insoluble. Hydroxides are usually insoluble except for group 1 cations, so sodium, potassium hydroxide are soluble, and chromates, so on. Okay, so these are rules that you either have to memorize or understand by using them often enough. Okay, so let's take a look briefly at how that shows up, looking at the precipitation of ionic molecules in solution, and these are reflective of these are, excuse me for a minute, these are reflective of other tutorials we've already done, looking at the concepts of precipitation and net ionic equations. If we have two solutions of soluble materials and we mix them, and we have an anion and a cation match up that are insoluble, we'll get precipitates. So barium chloride, go to the last slide and look at the solubility rules, is soluble. Sodium sulfate is soluble, but if we mix the two together, we end up with an insoluble material, barium sulfate, which will then precipitate out. So we can apply the rules shown in the last slide by taking two solutions of soluble materials, combining them, and then having to look at the ions in each of those solutions to see if we're likely to form a precipitate. And we can also look at the solubility of one liquid with another. So our solute does not always have to be a solid; it can be another liquid. And we're looking at solubility and the level of intermolecular interactions between the two molecules from the different liquids. When we're talking about liquid solubility, we're usually talking about miscibility as opposed to solubility. So if two liquids are miscible, that means they will mix. If two liquids are immiscible, that means they will not mix. Two vocabulary words that you should probably be interested in remembering. So if we take a look at a simple alcohol like methanol, that's wood alcohol, that's not drinking alcohol. Methanol and water, because they're both hydrogen bonding solvents, are infinitely soluble in each other, and they are completely miscible. Ethanol, exactly the same relationship. Propanol, exactly the same relationship. Butanol, now if we take a look at the formula for butanol, we see that we have a large portion of the molecule dominated by carbon-carbon, carbon-hydrogen nonpolar bonds, and that nonpolar section of the molecule does not want to interact with water. You can see now all of a sudden we can only dissolve 9 grams of butanol in 100 grams of water. And as we extend the size of that carbon chain, we extend the nonpolar characteristics of those molecules. We see that the solubility continues to drop. If we take a look at the reverse of that, we take a look at the solubility of an ionic compound like sodium chloride in different solvents. We see that sodium chloride is very soluble in a highly dipolar environment like water. As soon as we switch to methanol, the dipole has decreased, and all of a sudden there's very little ionic compound like sodium chloride we can dissolve there. And as we increase the nonpolar characteristics of that liquid, you can see that the ability of those liquids to dissolve ionic compounds decreases dramatically. Well, finally, we should probably talk about solution concentrations, since many of our calculations will involve concentration units. Often our units are in moles per liter, which we normally state as molar concentrations. But of course, anything where we have amount per volume is in fact a concentration, and we will see many different types of units, including grams per liter, milligrams per liter, parts per thousand, parts per million, parts per billion, and even for some calculations, we will need the number of moles of material per kilogram of solvent, not per volume of solvent. And that gives us a unit called molal. Typically, we use molal in calculations where during the experiment, we are changing the temperature of the system. Well, liquid volumes expand as we heat them up. So a concentration of moles per liter would be different at different concentrations because the liter volume changes. Well, in this case, then we end up using units of molal where the weight of the solvent does not change with temperature. We talk about dilute solutions containing a relatively small amount of solute, relatively being a qualitative term. We talk about concentrated solutions containing relatively large amounts of solute. We also talk about parts per mass in terms of part per thousand, part per million, part per billion. For a solid sample, that's grams of our solute or grams of our analyte per gram of sample. And we try to achieve those units and then multiply by a factor. So if we want parts per billion, we're going to take grams of our target compound per gram of sample and then multiply by a billion. Parts per trillion, we're going to do the same gram per gram and then multiply by a trillion. If we're talking about two liquids, then it will be milliliter of solute per milliliter of solution, again, times whatever factor. And then finally, for some environmental applications, we end up with mixed units of grams of weight per volume, grams per milliliter. In this case, we're always going to take our calculation until we have units of grams of solute per milliliter of solution, and then multiply by our factor. Parts per thousand will multiply by 1,000, parts per million will multiply by a million, and so on. Finally, let's take a minute to address the concept of electrolyte solutions. When we talk about electrolyte solutions, we talk about strong electrolytes or weak electrolytes. Well, let's start off with an example of a strong electrolyte. If we take sodium chloride solid and we dissolve that in solution, we end up with sodium ions and chloride ions. In fact, if we take 1 mole of sodium chloride and dissolve it in a liter of solution, we will get 1 mole of sodium ions and 1 mole of chloride ions. It will be completely soluble. Strong electrolytes not only dissolve completely in solution, but when they dissolve, they completely ionize, which means that we do not have any sodium and chloride ions still associated with each other in solution. They've separated from each other and they're associated with water solvent molecules. One of the features of electrolyte solutions is they conduct electricity. Well, that's kind of an odd way of looking at things. Why would we be interested in a solution that would conduct electricity? Well, one of the primary applications would be in batteries, where we have anodes and cathodes that are conducting oxidations and reductions, respectively. And the only thing between those anodes and cathodes is a liquid containing an electrolyte capable of shuttling positive and negative charges back and forth between our anodes and our cathodes. Well, let's look at another example. The organic molecule shown on the left-hand side of this equation is acetic acid. Acetic acid is normally identified in a kitchen as vinegar. And if we put acetic acid in solution, in water solution, we immediately set up an equilibrium between negatively charged acetate anions and positively charged hydronium ions, which we almost always abbreviate as hydrogen ions because we're lazy. But in this case, if I put 1 mole of acetic acid in solution and it will completely dissolve, I'll only get about 0.05 moles of acetate and 0.05 moles of hydrogen ion. The vast majority of the moles that I put in stays undissociated, not forming ions, in the covalent molecule acetic acid. So weak electrolytes dissolve completely in solution, but do not completely ionize. So I don't get to all the ions that I want if I'm interested in an electrolyte solution. Oddly enough, though, if we take an acid like acetic acid and we neutralize it with a strong base like sodium hydroxide and isolate the result, which would be a compound called sodium acetate. Sodium acetate is a completely ionic compound. And as soon as I throw sodium acetate in solution, and I can transform 1 mole of solid sodium acetate into 1 mole of acetate ions and 1 mole of sodium ions. It completely dissolves, it completely dissociates, and as a result, sodium acetate is a strong, gives me a strong electrolyte solution, as opposed to acetic acid, which does not.